Some buildings come to symbolize a nation, like this, and this.
And that. It's the Opera House that instantly put Australia on the map. Like other landmark buildings, it was enormously ambitious, and it used trailblazing building techniques. This incredible building has its share of secrets hidden in its engineering DNA.
It just wouldn't have been possible without a First World War gas mask, glue for false teeth.
OK, well, stand well back.
Ancient Egyptian woodcraft. A copper-bottomed sailing ship.
Whoa! Look at that!
And a collapsible toy.
Cut!
Even if you've never been to an opera in your life, you'll know this building, the Sydney Opera House.
At the heart of every great opera house and concert hall, obviously, is this. The stage, the seats, this is what it's all about. And from in here, well, you really could be anywhere in the world. But you certainly wouldn't say that about the structure around it. It's certainly not just a boring box around the stage. In fact, it's one of the most famous buildings in the world.
This building has such a famous shape that you could draw it on the back of an envelope and almost anyone would recognize it. Completed in 1973, the distinctive profile of Sydney Opera House instantly made it an icon of Australia. But construction had been troubled. Political wrangling led to costly overruns and delayed completion by 9 years. And the building wouldn't even stand up unless the designers had overcome formidable engineering challenges with some help from a collapsible toy. But more of that later, because when I said I wanted to get on top of the building to have a look around for myself, they didn't just point me to the lift.
There's a lot of safety equipment coming out here. Oh, there's more. Is this a hint?
I'm beginning to get that feeling when you don't quite know what you're in for.
How about that? But you'll be quite safe.
Quite.
Yeah.
So, with enough equipment for an Everest expedition, I set off. Maybe this is the way to the cheap seats.
I do like a night out at the theatre. Ow. Wow. That is staggering. Suddenly, you feel you really are standing on a piece of sculpture. It just takes the breath away. Just doesn't seem real. There are many, many theories about what inspired the shape of the Sydney Opera House roof.
Sails, nuns' hats, an armadillo.
Perhaps not. But whatever you see in these incredible forms, we do know that the architect wanted to create a magical space where you could leave everyday life behind.
The site itself was extraordinary. Previously a tram terminus, Danish architect Jørn Utzon aimed to make the most of its position right on the waterfront in the heart of Sydney. This is how it all started in 1956 with Utzon's rough sketch for a competition for a new opera house.
According to one version of the story, Jørn Utzon's winning design with these spectacular shapes wasn't even on the shore making constructions simple. His plan was for a vast magical space, a huge sculpture. He was the architect and he wanted concrete. it was up to the engineers to make it happen.
Engineer John Nutt was one of Arup's team of head-scratchers.
You know, if you're working with good architects, they will challenge you. And the last thing you want to do is say, listen, mate, you can't design this. It's not going to work. Because you know that somewhere there's a solution.
Arup knew that the magic of the design would be compromised with traditional concrete construction. They could never achieve the delicate shapes Utzon wanted. Arup's answer was to make a frame for each sail out of huge hollow concrete ribs. But it had never been done before on the scale required at Sydney. The biggest ribs would be fully 55 metres high. They were too big and heavy to mould in one piece. The principle behind the solution was child's play. Enter our first connection, a puppet.
This is the key. Well, not this particular giraffe, but the principle behind it, because toys like these are made of individual segments, in this case made of wood, held together with a cord. When you press the button on the bottom, it slackens the cord and the whole thing collapses. But let go again and it tightens up and the whole thing keeps its shape. And that is the principle they used when they built the Sydney Opera House.
Arup decided to make the huge ribs out of segments which could be pulled together to make the right shape, just like that child's collapsible toy. The technique is called post-tensioning. It also strengthens the concrete and was devised by a French engineer in the early 20th century to make bigger spans in bridges. Back at my workshop, Arup engineer Ed Clark shows me how it works.
So Sydney was made up out of precast segments of concrete. We've got precast segments here, not concrete here, polystyrene. So we're going to stack them up and build ourselves an arch.
OK, so we're actually going to recreate it here.
Yep.
You say it's on the, what, 1/10 scale?
1/10 scale.
It's still quite big, though, isn't it?
It's going to be big. It's going to be about 6.5 metres high. Sydney is about 60 metres high.
We start by building 2 stacks of blocks. The post-tensioning bit comes later, when you thread all the blocks together.
They actually are concrete, we're just very strong.
Soon we have 2 curved stacks of blocks resting on a steel supporting frame.
Right, they don't meet.
One more piece of the jigsaw to go in, the keystone, the most important part of the arch.
Next, we need to put in the post-tensioning cables, the sort of puppet strings that will hold the arch up.
Go.
OK, so I'll thread this in. The hole is in that plate there.
Indeed.
Well, there it is. I can see the other end.
Out at the bottom.
Brilliant.
Once the cables have been threaded, we need to tighten or post-tension them because it's still the steel frame that's holding the arch up.
Wow, so that really is... It's just resting.
When Ed's happy that the cables have been evenly tensioned, we're ready to remove the steel frame.
Looking good.
Right, so this is now getting rid of the fall. This is kind of a moment of truth for you, then.
It is
As
a little
lead
bit of a moment
engineer,
of
you're
truth.
lead engineer on our project. If it now all falls down, I'm the client, I'm going to be disappointed.
You were also the builder, though, so it could just come back.
As soon as that, yeah. Right, this is it. It's standing on its own or it's landing on their heads. Why are we backing off?
I'm not
if
sure.
you're confident?
I'm just following you.
Well, you're the engineer, you should know. It works.
She stands.
I think we've made something beautiful.
Ed wants to tension our puppet strings even more to increase the strength of the arch.
Is it possible that as we tighten it, we just squash the whole thing and it falls over?
Yeah, that's the danger, is that if we over-tighten it, of course, the polystyrene's only got a certain amount of compressive strength. The more we tighten it, the more bending resistance the arch has, but if we over-tighten it, the polystyrene could crush.
And is it the same with concrete?
It is the same with
Right.
concrete.
OK.
Finally, we're ready to test our post-tensioned polystyrene arch.
I think we should hang a test load from it and see.
OK. So that's a 20 kilogram weight. That's 40. I'm listening.
A little bit of a creak. Seems okay. I think we can go the same again.
Another 40?
Yeah, another couple of 20s on.
All right. This is just polystyrene.
Polystyrene and a couple of small wires. 7 metres in the air.
Ed is confident that the polystyrene can take a lot more. Another 70 kilos is loaded, bringing the total to 150 kilograms. And still, the arch stands strong. There's only one way to go. Take it to the limit. 240 kilos. That's half a horse, or 4 of me-ish.
Well, we're really not messing about here. That is a big stack of polystyrene blocks, post-tensioned with that narrow wire that we saw.
Carrying about 1/4 of a tonne.
That's staggering. I mean, I can't believe it can even hold its own shape, let alone support a 1/4 of a tonne. And seeing post-tensioning in action, seeing it built like that, it's kind of strengthened the link for me with my little friend the giraffe here, because you can see it's just a series of sections held together by the tension in the cable running through the centre of it. With no tension, it's just a pile of different bits. Put the tension in and it stands up. And that does give me an idea just for one last demonstration, I think, in the course of this experiment, which is what if, well, there isn't a button, but what if we take the tension out of that system?
We could do that. We could do that.
Yeah, I think we should. All right, chaps, this is in the name of experimenting. It's important work. Do it on go,
Let's do
I
it.
reckon. OK. I guess it's quite important we do this all at the same time.
Yeah, I think so.
More than quite important, it's absolutely critical we do this all at the same time. So, for all, apply our bolt cutters to the wire. I'll go 3, 2, 1, cut, and that's when we do it, all right? Then I suggest you run. Right. Everybody on the wire. Is everybody on?
Hang on. OK.
You on? OK. 3, 2, 1, cut! OK, well, we can safely conclude that it was the tension in these cables holding up that structure. Post-tensioning obviously works. The Opera House is still standing, and this would have been if we hadn't taken the tension out of it.
Making a huge concrete puppet allowed the Sydney engineers to build a complex shape, but it left them with a different problem.
The secret of cheap production is to make the same shape over and over again. You don't want lots of one-offs, different shapes and sizes, like the ones here.
It looked as if Sydney's sail ribs each curved differently and would need differently shaped molds. Expensive.
And then Utzon found the answer to building his magical space in this. Now, it wasn't a magic orange with the answer written in it. It was a shape. Because as he peeled the fruit, he realised he'd got it. Each of the sails is a different shape, but they could all come from one curve.
It's incredible, but if you took a huge orange 150 metres across, you could make the Sydney Opera House sails out of pieces of the peel. Each sail is a different-sized piece of the peel. Because it's the same orange, all the sails curve in the same way. So each of the different sail ribs could be made of the same curved segments, a few for the small ribs and more for the big ones. Production could be simplified. Sydney's roof construction began in 1963, but already the project was under strain, with political opponents sniping at Utzon over soaring costs. The project called for the then largest cranes in the world to lift the concrete ribs. A special kind of fearless worker maneuvered each segment into position. Sadly, one builder was killed. But even so, in 14 years of construction, often with no safety harnesses, that's still an astonishing record. They locked down each rib with huge steel cables, their own version of the puppet strings.
These great concrete blocks are the equivalent of the segments in my little giraffe toy. So the ribs were tensioned vertically to stop them slipping and horizontally to stop them falling apart. Oh, I haven't yet found a button you can press to release the tension.
And because squeezing the concrete also makes it stronger, it allowed thinner and more delicate-looking sails, perfect for Utzon's design.
Post-tensioning the sails meant the engineers didn't have to build huge columns inside the opera house, which would have been a bit inconvenient when you're trying to watch the fat lady or man sing.
But not even the tensioned steel was enough to lock everything in place. Heat causes the concrete to expand, and it contracts when it cools. Relentless swelling and shrinking could force the concrete segments apart. Not good for watertight joints. Worse, it puts an uneven strain on the post-tension structure itself, which could be a headache for opera goers.
The tiniest movement in the segments of the roof could have been fatal. One slip and this whole thing would have collapsed like a pack of cards. So it had to be, well, glued.
To ensure everything stayed in place, engineers needed a very special kind of glue. They had to look to dentures. These false teeth were made more than 2,000 years ago. A bulky metal brace holds them together. There was no good glue to hold teeth in dentures or opera houses up until 1936, when Pierre Castin produces the first epoxy glue and revolutionizes the world of false teeth.
Castin's epoxy created strong bonds, perfect for keeping false teeth in, which was good news for toffee eaters. But perhaps more importantly, it also means that can stay up.
Before Castin's dental revolution, glues needed surfaces to be absorbent, like wood. In the 1930s, a plane like the Mosquito bomber could only be stuck together with glue because it had a wooden airframe. The glue soaks in, making a strong joint. As planes evolved, designers turned to metal, which, just like the concrete in the opera house, isn't absorbent. Enter the pioneering Sea Hornet in the early 1940s. Sticking the metal in this plane needs a new kind of glue that forms a strong bond with the molecules on the surface. This family of new glues that form these molecular bonds includes Castin's epoxy. Back at my workshop, I've devised a sticky experiment to pit the kind of glue Castin devised against the old glue. Adhesives expert John Bishop helps me with the epoxy first.
Obviously, I just want to run around and chase robots there. It's like a sci-fi movie. Sorry. What do I do?
Right. Squeeze the trigger and put a bead up and down.
It's very nice. It looks very tasty. It looks like icing.
It does.
I'm tempted to write my name and happy birthday.
When the glue has set, it's time for a little test.
Don't worry about your car, by the way, John. It'll be fine.
It's going to go head-to-head with the wood glue used on the Mosquito aeroplane. Can either of them stick concrete or even metal?
So, first up, this is the glue that used to hold mosquitoes together.
That's the one.
Aeroplanes made of wood. Bring it on. Hopes high?
No, not at all.
Okay, well, it is a big ask.
Okay.
Right. In your own time, lift. Elevate. Okay, let's see how long it lasts. Oh. That hasn't gone then.
Oh, I did warn you.
You did. I didn't believe you, but that's not even tried, has it? Yeah, that's really not worked at all. In all fairness, it's not supposed to work on metal, but what can we learn from looking at it now?
It's got to penetrate the surface. This obviously hasn't done, so it's not going to work on metal. You can peel it off quite happily. That's why it doesn't stick, and that's why you don't fly in aeroplanes, metal aeroplanes that are stuck with this sort of glue.
And wood glue like that wouldn't have worked on concrete either. It simply couldn't have stuck the sails together at the Opera House. Take 2. Glue like cast-house denture epoxy, and apparently it's so much stronger that a much smaller area of glue should hold, even on metal.
So that's a quarter of the area.
Quarter of the area.
With the sticky stuff applied. Let's see. Bring it in. OK, well, let's stand well back and give it a shot. Well, that's clearly
That's holding,
quite happy.
even though it's rocking.
The Opera House was then the biggest construction ever to have used epoxy glue. The same epoxy that keeps teeth rooted in dentures sticks the ribs of the Opera House together and guarantees that they won't slide against each other when heating swells and cooling shrinks the concrete. The skeleton was complete. Now it needed a beautiful skin. Utzon wanted a distinctive surface, worthy of the waterfront position, one that reflected the constantly changing light. A Swedish manufacturer spent 3 years developing tiles specifically for this building.
There are more than 1 million tiles on this roof, and Utzon asked for 2 types, matte and gloss, and they were laid in intricate patterns and then fixed to thin lids made of chicken wire and concrete, which were then fixed to the concrete ribs, and the roof of the Sydney Opera House was complete.
But while more fearless workers laid the tile lids on the building, behind the scenes the project was in turmoil. The architect himself wasn't around to witness the completion of his iconic roof. In a furious dispute over rising building costs, Utzon walked away from the project in 1966. But construction continued. Ove Arup's engineers moved on to the next challenge.
Windows. Utzon wanted concertgoers to be able to see and enjoy the building's spectacular location right in the heart of the city on the harbour front. But there were 3 problems: the size of the windows, the shape of the windows, and the fact that you risk killing people if you use ordinary glass.
Just as the shape of the Opera House sails demanded innovative ways of assembling concrete, those same curves created new challenges for the window construction.
The holes to be filled weren't square, and they curved. And perhaps above all else, they were huge. Not really like windows at all, more like vast glass walls. Nobody had ever done anything like this before, not on this scale.
The designers wanted massive windows to allow the light to flood in, but big panes of ordinary glass are weak. Relatively small shocks can shatter them. Nobody wants 4-metre-high windows falling onto opera goers. It took a deadly threat back in the First World War, poison gas, to point to the answer. Without gas masks, it just wouldn't have been possible to build Utzon's Opera House safely. The same invention that would prevent the glass eyepieces from shattering and blinding soldiers will come in handy when making Utzon's vision a reality. To see why normal glass is not such a good idea, either for gas masks or the Opera House, I visit one of the biggest glass makers in the world. Glass expert Susan Lambeth of Saint-Gobain has got a big sheet of standard glass for me.
Okay, well, this is a piece of 10mm thick float glass. It's what we make here every day, float glass like this.
So what might you use a piece of glass like this for?
It could be typically used in windows and facades and some roofs and things like that at this size and this thickness.
So this is just a big piece of standard glass as it comes out of the manufacturing plant just over there.
Over there, exactly.
In its most basic
In its most
form.
basic form, yeah.
This is good glass, as used in ordinary buildings all over the world every day. We're just going to test it.
These are important. This is part of the whole test. We'll just put these down here for now, I think.
Okay.
Meet our opera goers. I'm going to drop a tile about the same size as the ones on the Opera House from more than 10 metres. Remember, in reality, the Opera House is 55 metres high.
Here goes. Please hit it.
Yep, it's fine.
Not a scratch. You see, this is good glass. But of course, everything has a limit.
Now for the big one. I'm not actually being as brutal as it might look throwing a brick through our window, because I've done the maths, and this brick from this height, 11.5 metres, onto the glass will have about the same impact as one of the roof tiles falling off the tallest shell at the Sydney Opera House onto a piece of glass. You see? It's sophisticated. I just need a brick. Below! Oh dear. Sorry I broke your window. I'm sorry.
Let's go have a look.
I feel like I should say, can I have my ball back now? Oh, it's gory. Things don't look good for the watermelon audience
No,
in
they
the Opera
don't.
House. The thickness of that glass, I mean, that was a substantial piece of glass.
It was, yeah, it's pretty gruesome.
That glass is perfect for everyday use. But at Sydney Opera House, this would have been carnage. There is a solution, as used in World War I gas masks: laminated glass. Amazingly, it uses exactly the same standard glass, with one tiny little difference. Back at the factory, the glass starts its life in a fiery furnace, where the raw ingredients are mixed and baked. 800 meters later, the continuous sheet is cut into panes. The secret is to make these panes into a special sandwich. A thin film of plastic polyvinyl butyl, or PVB, is sandwiched between the two panes of standard glass. The result? Laminated glass.
And this whole process of making a glass sandwich was discovered by accident.
Rewind to a French laboratory in the early 20th century. A clumsy scientist knocks over an empty chemical flask. Miraculously, it doesn't shatter. Nobody has cleaned the glass. The broken flask holds its shape because of an almost invisible film of sticky cellulose nitrate inside it. The idea of laminated glass is born. Cut to the First World War. Troops need protection from deadly poison gas attacks, so the gas mask is born. But as we've seen, bombs and shrapnel mean standard glass in eyepieces can create the kind of splinters which can split watermelons. Laminated glass sees action for the first time. But is it good enough for Opera House windows?
Well, let's put this stuff to the test in the simplest possible way. I'm going to start off where the last glass failed, the brick.
Remember, this would be a tile falling from 55 metres, the height of the top sail.
OK, here goes. 3, 2, 1.
But it didn't even bother it, did it? Felt like I was throwing bricks at somebody else's greenhouse, but it didn't even scratch. I mean, it just bounced off.
This, of course, is a lot heavier.
More than 7 kilograms. I know bowling balls don't tend to fall out of the sky, but you get the picture.
3, 2, 1.
Just as in our demonstration, Sydney's laminated glass consists of 2 panes separated by a layer of PVB. But they're even thicker than our test sheet. So, no worries about bowling balls falling out of the sky. Now concert goers can hold a glass in their hands without fearing glass falling on their heads. The structure of the Opera House was complete. It looked good. Now engineers had to make sure it sounded good too.
Concrete was never going to be suitable for the actual concert hall. The concrete shapes and the material itself are just completely unsuitable for an auditorium.
Inside the shells, there are tall, pointy voids. The voice of even the strongest singer would have disappeared in there.
Which is a bit of a problem, you might think.
Even worse, concrete is acoustically harsh. It reflects sound as a mirror reflects light.
The designers needed to create an interior with a completely different shape out of a completely different material. Something like wood.
Its shape had to be curved to bounce sound back down, but they needed a special kind of wood. Ordinary wood wasn't light or strong enough to do the job, without a huge frame to hold it in place. An ancient pharaoh's mummy pointed to the solution. Tutankhamun's tomb was discovered in 1922, along with something much more important for the Sydney Opera House. Among priceless ancient Egyptian artifacts were ingenious wooden chests. Despite the fertility brought by the mighty Nile, quality wood was in short supply. To get round this, ancient Egyptian carpenters faked the appearance of fine wood. Tutankhamun's chests were made of layers of poor wood, faced with a thin veneer of rare wood.
In other words, it was plywood. Now that probably comes as a bit of a surprise because plywood frankly has something of an image problem as workaday stuff, but it can be used for furniture, like this chair, a modern day classic. Obviously, it looked better when Christine Keeler did it.
Utzon believed plywood was good for more than just furniture. He thought it could work on a huge scale to create the perfect interior for the Opera House. The key to moulding the complex shapes inside the concert hall was the way plywood is constructed.
Wood is much stronger in one direction than another. That's why it's easy to split along its grain. It naturally goes that way. The key to plywood strength is to use different layers of wood with their grain in opposing directions. And as a result of that process, a given thickness of plywood is stronger than the same thickness of plain wood. You need less material to do the same job. It's lighter. Thing about plywood, it might look ordinary, but it's got hidden strengths.
Let's see. I'm going to try to make something that's light and strong. And I'm going to think like an Egyptian and make it elegant as well.
Plywood. This bridge has been constructed entirely from it, by layering, laminating different sheets of it to form that graceful curve. But plywood isn't just about making beautiful shapes. And it is a beautiful shape. It's also surprisingly strong. Not bad, but I'm not done with this bridge yet. The bike weighs 50 kilos, and I'm another 69. Well, 70. 71. The wood bends, but it springs back effortlessly. Those ancient Egyptians knew a thing or two. The interior of the Opera House is like a separate building inside the concrete shell. You can get to places up in the roof where you can see you're between the two structures. Stagehands call this the Bombay, and that is the auditorium down there, quite a long way down there. And it means that I'm sandwiched between the roof, the plywood shell of the auditorium down there, and the concrete shell up there. Plywood was good for the interior because it's naturally acoustically kinder than concrete. And being light and strong, it could make a separate shell inside the concrete sails. Best of all, as Tutankhamun's craftsmen knew, it can be shaped. The right curves mean it reflects sound back down so the audience can hear what they've paid for. So that's how you build an opera house, outside and in. Except there's just one more thing. Because, yep, it's a beautiful sculptural thing in a spectacular setting. And it's a place where concertgoers really can just escape from reality. But how do you make sure they're comfortable while they're doing it? Well, the answer lies down there. On any given night, the Opera House can host not just opera, but ballet, drama, and concerts of all kinds of music. Every morning, the theatres come alive as technicians prepare the stages for the shows. They check sound and rig lights. But a perfect performance requires something else. It's a warm summer's evening on the Sydney waterfront. People can wait months for tickets, and it ought to be a beautiful night out. You come into this extraordinary building. The excitement in this room around you is palpable. You're full of expectation. You take your seat. And then, no matter how hot the performance, if there isn't good air conditioning, you're going to be in misery. A room full of thousands of people heats up very quickly. Why should we care about all of this? Other buildings manage their air conditioning needs perfectly easily without making a fuss. Well, the answer to this takes us right back to where we started. That distinctive and unique shape, the sails. This outline just wouldn't have looked the same with a chimney, or a fan deck or cooling towers poking out of the top, which is what large air conditioning systems usually need. So they needed a different solution. Thanks to a copper-bottom sailing ship, the answer was all around them. All air conditioning systems need somewhere to get rid of the heat. If it can't go up a chimney, where does it go? Facilities manager Bob Moffat takes me underneath the Opera House to show where they find an inexhaustible supply of something to take the heat away from the Opera House. It's the water from Sydney Harbour. This is seawater.
Indeed.
So this presumably is the start of the whole thing, is it?
That's right, this is the start. Basically, just over there underneath, you'll see that that's the seawater intake tunnel.
Yeah.
It's about 1 metre high. It's where the water will enter into the building. And the air conditioning process starts from there.
I want to see how seawater can cool a theatre. Bob takes me into the bowels of the Opera House. The seawater that we saw has come in here.
It has.
And what does it do? What happens to it then?
It comes into these vessels here where we have the seawater and the fresh water, both in independent circuits of each other.
Inside this large vessel are two sets of pipes carrying seawater and fresh water in completely separate circuits. Heat from the air conditioning system is brought out by the fresh water and is transferred to the cooler seawater. They never actually mix.
The seawater comes in on this side, cools down the water that's inside the vessel, which is the fresh water, and goes out on the other side, out to the ocean.
So that's it, it's not a lengthy stay for the seawater, it's in, cooler and out.
Yep, very quick.
But during that short visit, seawater can wreak horrible damage to the Opera House's expensive pipework. It's really corrosive stuff, which brings us to sailing ships. To protect 19th century wooden ships from wood-boring pests, the British Navy shields the hulls with copper. When they add the copper, they find that the iron nails holding the boat together rust. Fascinatingly, it's all to do with electricity, as corrosion expert Robin Oakley shows.
Here's a piece of copper and here's a piece of zinc, so they're two different metals. Now, put them together dry and there's no electricity flowing between them. However, if I put a bit of salty water between them...
So it's just salty water in that cup?
It's just salty water, just soaked into this piece of blotting paper. Make a little stack.
So now they're effectively just sandwiched... Well, the seawater is sandwiched by the two different metals, that's it?
Yes.
OK.
And what I'll show you is we have volts flowing.
And it's the seawater making that possible because it's an efficient and effective conductor.
Connecting two metals in salt water makes a primitive battery cell. The bad news for ships and opera houses, it also makes corrosion. I'm going to show how some metals are prone to corrode, while others resist it strongly.
The most resistant metal like that is gold. Doesn't corrode at all. Because that gold's called a noble metal, and metals that are less noble or active want to corrode.
So copper
is quite noble. Quite noble.
You didn't bring a sheet of gold, I noticed.
Didn't bring a sheet of gold, didn't think the budget would run to it.
It could be difficult. OK, so that's quite a noble metal.
Yes. What you've got is a more active metal. So we've got the painted steel plate with a suitable
I see what you've
motif.
done. That's our opera house, yes, which you painted on. So how will that affect things?
Well, what will happen is the electrical current that's caused by the two metals is focused into the bare metal parts.
So if we get an effect at all, we'll get an effect here.
Yes.
The next step would normally take years, but we're all busy people, so we're going to speed this up a bit with a car battery. Fast forward 1,000 times.
We're going to accelerate the process in its natural direction, but just harder and faster.
Is this bit dangerous?
Relatively low voltages.
Good. Relatively.
That's relatively low.
Plus it's you doing it.
And it's me doing it.
So that's now why... Whoa! Look at that! Why is that? What's happening?
The copper plate isn't corroding. That's not corrosion. Corrosion's happening over here, but a bit slower. That is gas. We're actually breaking the water apart, and it's giving off hydrogen gas, which is always spectacular, and you can see it.
24 hours of furious fizzing later, and we have 3 years' worth of swamp.
So this is it. Now we find out what's happened.
Well, obviously all this stuff on the top, this is all basically rust. This is, the steel's being corroded.
It looks terrifying in there.
Yes. And now we'll find out exactly how much this accelerated corrosion has done to that
a
plate.
steel plate. Whoa! Look at that, coming clean through.
Yeah, I mean, corrosion has eaten away the Sydney Opera House out in the middle of that plate.
Quite badly.
So this is an example of how mixed metals in a conductive liquid like seawater, the electricity you get can be destructive and cause corrosion.
The steel is eaten away because it's more reactive, less noble than copper. You protect the steel with a metal that's even less noble, which is sacrifice. We've got another tank that's fizzed for 24 hours with the same copper and steel. Only difference? Some sacrificial zinc.
What we've done here, we've got the same setup, we've also got a zinc block, which is electrically connected to this steel panel.
So you've introduced a third metal in there, then?
Yes. Let's see what it's done to the steel plate.
So disconnecting that plate, and it hasn't eaten through, I mean, nothing.
No,
It's done nothing to it.
It's fine. It's just got a little bit of slime on the surface.
And the difference in here is that zinc block.
Yes.
How's that work?
Well, the zinc here has actually been corroding preferentially. It's been sacrificial to the steel, Actually, this isn't the original zinc block. That's been eaten away already. We've had to replace it.
So this whole thing becomes a system then, if you like, and you introduce that zinc into it. The zinc really wants to corrode more than anything else in that system, so
Correct.
it takes the hit.
To stop those iron nails in copper-bottom sailing ships corroding, they protect them with a less noble metal. Sir Humphrey Davy attaches zinc to the hull. It's sacrificed and renewed as necessary. And in Sydney, they protect their steel pipes from salt water by putting, yes, replaceable sacrificial zinc in the seawater circuit.
This is the zinc blocks that we actually use to control that corrosion.
So that's what protects it?
It is.
So this is then eaten away by this corrosive seawater. How much of it will it eat away?
It'll virtually be all gone. You'll only be left with this small piece of steel which holds the block on.
So that whole lot will go in how long?
In 12 months, that'll all disappear.
All eaten away, and that's protecting it all in here?
Protecting all the steel inside the heat exchangers.
Billions of litres of seawater have passed through the Opera House in 35 years of operation, but its air conditioning system is still uncorroded. Sydney opera goers can bathe in the music, not their own sweat, thanks to some bits of zinc on a copper-bottom sailing ship. Best of all, Utzon's magical space keeps its distinctive profile.
Whether those are sails or nuns' hats or seashells, that beautiful building connects Sydney with its beautiful harbour. Jörn Utzon gave Australia a design for a new opera house, but without Ove Arup and his structural designers, we would be without one of the most distinctive pieces of modern architecture anywhere in the world, Australia's landmark building.
And Utzon and Arup couldn't have done it without a collapsible toy, a clumsy scientist, false teeth, a pharaoh's chest, and a copper-bottom sailing ship.